given a circle with AB being the diameter and CD being perpendicular to AB, and you need to prove that CD squared is equal to AD times DB. So taking a look at this equation, you can tell that there will be some kind of proportion involved, because you're talking about CD being multiplied to itself in order to produce the square and being related to AD and DB somehow, right? So we're going to be talking about similarity of triangles. So if you prove that, the similarity of triangles, it will be relatively easy for you to prove the final statement. Okay, so the first thing, of course, is to copy down the given. AB is a diameter, and then CD is perpendicular to AB. Okay, so this is given. Now the next part is to see that first of all ADC and CDB are right angles. Why is that? Because we're given that the CD is perpendicular to AB, right? So ADC, angle ADC and angle CDB are right angles. Okay, so this can be explained as the definition of right angles. Definition of right angles. So now, the next part, you want to notice that ACB is also a right angle. Is a right angle. Why is that? Well, actually, before you do that, you have to point out that it's an inscribed angle, because that would be kind of like skipping a step, right? It's an inscribed. It's an inscribed angle. An inscribed angle, and how do we know that? We know that it's at the point C, and that's on the circle. Okay, so we can just say that it's definition of an inscribed angle, right? So the definition would say that basically the vertex where the angle is at is on the circle. Not inside the circle, but on the circle. Okay, so now the next part now is to say that the ACB is actually a right angle. Now, how do we know that? Notice how this angle intercepts an arc that makes 180 degrees, right? Because AB is a diameter. So thus, since 180 degrees, the inscribed angle takes 1/2 of that, so it must be 90 degrees and therefore a right angle. The shortest way to explain that is to say that inscribed angle is subtended. You can just say inscribed angle subtended by a diameter. That's just a short way of explaining it. Now, the fifth statement is to say that notice that we have a couple of right angles, a couple of pairs of right angles, actually 3 pairs of right angles that we should indicate being congruent. ADC and CDB, ADC, angles ADC and ACB, right? So ADC, that was a right angle, we noted that. CDB, right angle, so these are congruent. ADC and ACB, because that inscribed angles was 90 degrees as well, as that was a right angle, as we just noted before. And then finally CDB being congruent to ACB, right? Because CDB is also a right angle, it's congruent to the inscribed angle as well, right? So we can say that explain it as right angles are congruent. Okay, the next part now is to notice that CAD. So what we're trying to do, we're trying to show similarity. We can use angle-angle similarity, right? To get there, we need one more pair of angles that we find the same. So notice that CAD is congruent to CAB, right? So we're basically trying to determine similarity of this small triangle and this largest triangle. And notice that they both share this angle and they both share a 90-degree angle, right? As we've shown in this step. Right, so ACB or BCA, however you want to say it, is congruent to ADC. That's one pair, and the second pair is this shared angle. But we can name it as CAD is congruent to CAB. Right, so CAD congruent to CAB because that's the same exact angle. It's just a different way of naming it, right? But the angle doesn't change. Now another one is CBA is congruent, so CBA is that one, is congruent to itself, but we can name it as CBD. CBD, right? That's the same angle, but it happens to be a different triangle, and that's great, right? Because we're trying to determine similarity, right? So two pieces of similarities that we're trying to determine. Now we can explain it as simply the reflexive property of congruence, right? Because we're talking about the same angle, right? CAD is the same as CAB. That's the same angle. That's why it's reflexive. Reflexively, they're congruent, and CBA is the same as CBD. That's the same angle. Therefore, it's reflexive. Okay, so now guess what? We've already shown that this triangle and the largest triangle, the smallest and the largest, shares two angles that are the same, 90 degrees in that one. And also the second largest shares two angles with this largest triangle as well, right? So that's already enough. The angle-angle similarity is already enough to conclude that we have two pairs of similar triangles, right? So triangle ADC is similar to triangle ACB. And CDB triangle is similar to triangle ACB. And again, this is the angle-angle because each pair shares two angles. So angle-angle similarity postulate. That's going to be the reason. Now we're ready to say that since ADC is similar to ACB and CDB is also to ACB, that means that these two, ADC and CDB, are similar as well. This is the transitive property. So ADC is similar to CDB, right? And we can explain it as the transitive property of similarity. Okay, now the ninth step is so we already showed that ADC, the smallest triangle, is similar to CDB, the second smallest. That's great, because now we can use the proportion of sides of respective sides and use the fact that there will be a scale factor involved transforming AD into CD and CD into DB, right? Because we already showed that these two triangles are similar, so therefore we can use proportion, right? So thus AD divided by the DC, well, CD we should say, not DC, is equal to the smallest side of this triangle, which is CD, divided by the second smallest side of this triangle, which is DB, right? That's how we did with the smallest triangle, right? We start with the smallest side, AD, divided by the second smallest. Now we have to start the same way for the second smallest triangle, CD. Second smallest triangle, smallest side is CD, divided by the second smallest side of the second smallest triangle, which is DB, right? So that's DB, right? And we can explain it as, of course, corresponding sides of similar triangles are proportional. This is a very important reason that you should remember to use. Corresponding sides of similar triangles are proportional. Now the next step is to, of course, cross multiply, because guess what? Look, if you cross multiply, we're kind of heading to the proof there that we need to get to, right? So AD divided by the DB is equal to CD being multiplied to itself, CD, right? And this is cross multiplication. How do we explain that? The means, extremes, property of proportion. Okay, means extremes, property of proportions. So now finally we need to simplify. Understand that the CD times itself is equal to CD being squared, right? And the simple reason for that would be to say definition of a square number. And this number can be a quantity, anything that's being squared, right? So this is the definition of a squared number. So now CD times CD is CD squared. So now we can use the transitive property. Since AD times DB is CD times CD and CD times CD is CD squared, then we can use the transitive property and look at this diagonally and say that AD times DB is equal to CD squared. Okay? And this is, of course, the transitive property of equality. So now finally, you can't leave it like this because you have to show the correct order. The CD is to the left, right? Not to the right. CD squared is to the left in your proof. Some professors or teachers might accept this if you finish there, but I would recommend to fully give this a very legitimate proof, right? So switch sides. CD squared is equal to AD times DB. And the simple reason for that is to simply say this is the symmetric property of equality. So as you can see, this was a long proof, but it was a very interesting proof. I hope you had a lot of fun and learned something. Thanks for watching. See you in the next video.